Hello, welcome. Just a second. Hello, welcome to my live stream. I hope the music is looking good. It's not too loud, and I hope that the sound is good. Now today I'm streaming from a different computer, and I hope that everything works well because it's the first time I'm streaming from this computer. The only issue I have right now is I don't have a proper graphics card, so I had the one I have crashed a few times, and I hope it's not gonna crash today. Yeah, so welcome everyone. Thank you very much for joining me. Today the plan is to basically continue what we started 2 live streams ago. We started to refactor all the code and rewrite large parts of it in C++ because C++ is better in many ways, and personally I like C++ a lot more, and I've gone into detail about why I did this in my previous live streams. Okay, so where are we right now? This right here is the code that we've worked on in the last couple of live streams, and this is the old C code. And the way I've kind of gone through it is to basically go piece by piece. We started with the text devices, with the printing text to the screen. That's a pretty important feature, I suppose. All the debugging stuff. Then we've done the disk and a lot of the disk stuff. And now we are here at this fat initialize, basically. This is where we are at. And today we're gonna basically put the fat file system in a nice C++ class. And maybe even the elf loader. Let's see how far we can get into this today. Okay, so yeah, in the previous videos, the way I kind of designed this is I have this core library, which is a static library that gets linked into both the bootloader and the kernel. And a lot of the shared functionality like debugging and like printing debug messages, like the file systems, these are shared functionalities between them, and it kind of makes sense to not write this code 2 times, just write it once. Okay, so let's start by thinking about how to design a file system, because this is basically what it comes to. So previously, let's take a look at what we had here with the fat function. So with the fat functions, we had an initialize method, obviously, for creating the file system itself. Then an open method, which would be used to open a file. Read, which was used to read a file to basically read data from a file. Read entry is used to read the files, the directory entries, more exactly. So in case we open a directory, then we would use fat read entry to go through all of those files, all of those entries inside that directory, and then we have close, which just cleans up all the resources. And I think this is a pretty good start, and we kind of want to have most of these. But we're just gonna make them so in a way that works very well. No, they will work well for any file system, not just fat. For example, one of the issues we have here is this fat attributes. These are specific to fat. There are some similar things in ext, for example, but things are a bit different there. For example, for hidden files, there's no attribute in ext. It's just a file that starts with a dot. So the period, the dot sign in front of a file name means that it is hidden. All right. So let's see. Okay, so let's go here in file system and create file system.hpp and think about how to design this. Pragma once. This is the include guard. And now let's see. So class file system. Now a file system normally is used to own a block device, basically. So the way we've structured these devices is that we have a character device, as I discussed the last time. A character device is basically a device like in which you kind of communicate both ways. That's the idea of a character device. And then we have the block device. The block device has similar functionality to a character device. You can read and write data to it. However, a block device is more like a random access device, like for example, a hard drive, where you can basically just go anywhere, you can seek anywhere you want and read data from there. So that is the difference between a block device and a character device. And of course, a file system makes sense for block devices. A character device would be more appropriate for things like the serial port, for example, or USB communication. You're basically having a two-way communication with the device. You're sending a command and receiving a response. So that's the idea for a character device. A block device, as I said, it's more like a random access device where you can access data wherever. Okay, so yeah, for initialize, we can just use the constructor, although, okay, let me think about this. Okay, so we also want to have a way to probe file systems. That's kind of something that we don't have right now, and we will want to have in the future. And that's probably a good idea, because whenever we open a disk device, we don't know what file system it has on it. It may have FAT, it may have ext, so there has to be a way to detect all of these file systems, and the best way to do that would be to basically have an initialize method here that also does a probing, so it verifies that all the data makes sense. Basically, that's kind of how this works. For example, let's see here the FAT OS dev. If I go to the OS dev wiki for the file allocation table, and you have these data structures here, and the way you can verify you can actually do this probing is by checking these values from the headers and verifying that if they make sense. For example, and it doesn't have to be like it has to go through all of these filters. You can also have heuristical stuff. For example, this okay, there were that string. Okay, let me see which one is it. Okay, so there's here, I think in the extended boot record, there is this system identifier string, which is a representation of the FAT file system type. So it will say FAT12 or FAT16, FAT32. And yeah, that can basically add points. If you find this, then okay, it's likely to be a FAT file system. But it's not, you shouldn't use just this field. You should use multiple fields to verify. You should make sure that, I don't know, maybe the number of sectors per cluster, it makes sense. Maybe the number of file allocation tables makes sense. I mean, it's most likely that you have 2 file allocation tables. Maybe there are exceptions. Maybe there are maybe there are operating systems or formatting utilities that use that format using multiple file allocation tables, like 3 or 4. But 200, that doesn't make sense. So you can use that to verify this information. Maybe the media descriptor type could also be something you could check. Okay, so all the valid values are between E5 and FF. And if it's not one of these, then you can say, okay, maybe this isn't what we're looking for. Yeah, so that's the basic idea about these checks. Now, obviously, the annoying part here is that you kind of have to figure out which fields are important and which are not. Okay, so let's start with the bool initialize, and we are going to take a block device. Okay, and then we just say equals 0 because this is a pure virtual method. We're not going to actually implement it here. We're going to implement it inside the actual file systems. Okay, so okay, this one should be virtual. What else? Okay, I think this looks pretty good. Okay, then we have okay, so we need a way to browse files. Basically, we need to figure out what files are present on a disk, and okay, let's see. Okay, so for that we will probably need a different structure, like struct file entry, and then I don't know, we will think about what makes sense here to add. Maybe a name. Now the name here is okay, so usually on Windows you are limited to 256 characters. On Linux I think it's like 4K, 4000. So I don't know. Anyway, I'll figure this out at some point. You probably want to have some attributes. So let's see. Enum attributes, file attributes. And the reason why I'm not making this an enum class is because enum classes aren't very useful for flags. Yeah, okay, that is ugly. No, I'm not gonna do that. I'm just gonna use enums, normal enums. Okay, so we can have attributes like, what would make sense here, like a file or directory. In fact, let's have that as a separate enum class, file type, and we can have file or directory, and of course link and all of those. But for now, let's just keep these things simple. Okay, we will think about the attributes later. I don't think it's that important to do this right now. Okay, maybe read only might be useful. But yeah, we'll figure these out later. Alright, so we have an initialize function. Now let's see how we can browse directories. Something that would make sense would be probably to do like to have maybe like so there are two ways of doing this. I'm thinking maybe one of them is to do like get file count, and then And of course, file entry should be the parent. So that's one way to do it, to get file count and then get file and entry and have an index. But what I'm thinking is that that might not be the most efficient way of going through them, of looping through them, because you might have to do lookups. So, okay, let's just do it the other way, which would be kind of like the way we did here. So just have a Boolean method, read next entry. So, okay, let's just say get next file entry. Okay, and we will need the parent basically. And then we also have like a previous entry, which is initially set to 0 or to null, in fact. And I think this looks pretty good. So the way this would work is that okay, so this one cannot be a Boolean, it has to be like this. So we are returning a file entry and we are receiving the parent directory. So this way we know who is browsing that file basically. Okay, so yeah, the way this kind of needs to work is kind of like an iterator. And what I'm thinking here is that if we have to do this in parallel, for example, if we want to have multiple threads getting files, then we will have a bit of an issue with this. But that's my main concern right now. But I think we should... Okay, I'm just gonna leave it like this for the moment, and because we're not gonna have threads, at least not yet. It will take a while until we get there, and a lot of things will need to change when we have multiple threads. There are gonna have to be a lot of synchronization methods, and a lot of resources will have to be managed properly in this multi-threaded context. So I think for now it's okay to just leave it like this. Okay, so yeah, get next file entry, and we will receive a parent or maybe null pointer for the root directory, and then the previous, so that we can iterate over the entire list. And I think that makes sense. Okay, so then we will want open, read, and write, basically. And for this, we should use this file class that I have created. Open, and what we want here is... so for the file system, I'm thinking about how to do this. So for the file system, I don't think we actually need to yeah, so the virtual file system will take care of browsing subdirectories, so I think it's fine to just have open work with a file entry. I think that would be just the best way to implement this, because we have that parsing of paths, which is something that's going to be common for all the file systems, and I think the virtual file system is the best place to do that. Okay. And we will also want to have a mode here, so enum file open mode. Open, read, okay. Read, write, append, and maybe more. We will see. Okay. And then what else we had here? So we had read. This one makes sense to implement in the file class, and then close, which will also be in the file class. Yeah. Yeah, Andrei, you expected that I only use classes and namespaces. Well, inheritance is kind of part of using these classes, and I think these are very useful abstractions, because that's the main reason why I wanted to move to C++. These things are very difficult to do in C. Now, as you can see here, I will show you an example of how I am using this virtual stuff. So basically what I have defined here, this file system is an interface, because all of the methods are pure virtual. All the methods are virtual, so we're not implementing them here inside the file system class. We're gonna have, for example, the pat file system class, which will implement include file system, and then we will create class pat file system. Doing things this way is going to allow a lot more flexibility than if we don't use these features like virtual. And the const expression is basically just a way. So, you know, for example, I have const int a equals 10. But if I want to create a variable, for example, array of a, then the compiler will not let me do this. It's gonna give me an error. And this is why const expression exists. Because const is basically putting this piece of data, it's putting it into the actual file, into the actual binary, in that read-only data section, for example, or in that, yeah, this is a const, so it should be in that read-only data section. And yeah, even though we set const here, this is still a piece of data which exists in the file. And in theory, we can even modify it, so we can do hackish stuff like, I don't know, const cast, for example. And we will just cast this a to an int pointer, which is not const. But now we can actually modify the data there. And this is why the compiler will not let me do this. And this is why we use const expression. Const expression means that this expression is going to be constant at compile time. It's not going to change ever. This is meant to be constant at compile time. And now the compiler will let me do this. So this is why I use const expression. Yeah, if you have any other questions, Andre, you can feel free to ask. I will explain all the concepts if you think that will help. All right, so now we are going to add these methods. And we are going to override them. It just means that we're going to implement them here. And we are also going to have some private stuff, and we will see in just a moment what kind of stuff we will have here. So obviously we need to save the block device, so let's do that. And now let's implement this class. Add file system.cpp include, and let's start with this initialize function. Okay, so all that we have to do here is just set the device to device and then run the detection. Now, for the moment, I'm not gonna have any because at this moment we only support fat, and we're just gonna return true. Okay, and we will also need a constructor to initialize this to null at the beginning. Okay, it's just good practice to do this. How am I? I'm very good, thank you. Yeah, I'm very good. Just trying to make videos. Yeah, I've been working on that memory management, on that first memory management video for like 3 weeks already, and I'm still not finished, so yeah, a bit struggling with that, but other than that, I'm pretty good. Thank you. How are you? Okay, so I've just added these implementations here that we will work on. Okay, so let's start with this one, get next file entry. So the basic idea here is that okay, let's start with open. In fact, I want to start with open because I think this one's a bit more straightforward. This one requires a bit more work. Okay, so we're gonna start with open. Oh, you'll get there. You'll get there, Gregory. You will get there. Don't worry. Okay, so now let's go into the actual implementation of this fat open. Okay, Visual Studio Code is not cooperating here. Okay, so okay, there's a lot of stuff here. A lot of headers. Okay, what I'm gonna do is I'm just gonna copy all of these headers inside over here. And we can get rid of this type def because it's no longer necessary. And yeah, let's just clean this up a little bit. Now, the thing is, okay, we will probably need to have some specific files for... Okay, we're gonna split this implementation into a couple of classes here, and for that, let's just create a folder, fat. Because this is gonna have more files than I thought it would. So the first one will be a fat file.hpp, which will inherit from this file. Now, what we're going to do here inside the fat file system, when we call open, we will basically create a fat file and we will return it. And the user will, I mean, whoever uses this, will not see all the internal implementation details for how a fat file works, but they will only get the actual interface that we want to expose. Okay, so I kind of have to add here Yeah, so we also need the fat file entry and entry.hpp, which will also have an implementation. So let's just have fat headers.hpp. So I'm gonna put all these headers in the file. It makes a lot more sense. Yeah, now this is gonna be a lot of work, but yeah, we will make it work. We will do this right. Okay, we can get rid of this. Why am I using fat? Because fat is easy to implement. NTFS is a very complex file system. That's basically why. Okay, now I also had this file data, which I used to keep the information about a specific file. Okay, I think we might not need this anymore. And this long file name block, we will think about what to do with this one later. Okay. A lot of work for later me. Alright, so also, yeah, this file data and this long file name block, we will have to rethink a bit. Okay, so let's start here with open. So in order to open a file, we basically need to get that file entry, and which will basically just contain this fat file entry. It will just contain that structure. Okay, so I forgot that I actually do a lot of stuff here in this fat initialize, and we should do that here as well. So let's do these things as well. Okay, so I'm kind of still thinking about how to split off this this huge fat stuff, because it's gonna have quite a lot of stuff. Yeah, so something that I think we can change is that we will not need to... Yeah, so here in this fat driver, one thing that I did here was to keep track of the open files, and this is basically what this file data is. And this is something we won't have to do here anymore. This is something that belongs in the virtual file system. Okay, so I'm kind of thinking how to do this. Okay, so yeah, let's do fat initialize first, and then we will think about the rest. So the first step I do here is to basically use this piece of data here. Okay, this is something we won't be able to do. And here is where things get a little bit more complicated, because in the stage 2, for example, to read the boot sector, we just read it to this memory fat address, which is a constant. But in the kernel, we will want to go through the memory manager probably. And that's something to keep in mind here. So what we could do is to basically implement some way of allocating blocks of memory. I'm kind of thinking how to do this. What would be the best approach that's not gonna be difficult to change later. Because we basically need yeah, we need to allocate quite a lot of data, so for this stuff. Something that I'm thinking of. So what we could do is to create like an allocator class. That's one thing that I was thinking about, but that would just get complicated and unnecessary. Because once we have memory management, we can just use new, which is probably going to be a much better idea anyway. Yeah, this is a kind of annoying. Okay, so the way I can think about the way we can do this is to basically have some memory reserved here. So whenever we create this fat file system, to basically require that the whoever instantiates this class to give me some memory where I can use to basically allocate some memory. Okay, so let's take that approach, and whenever we will have the memory manager, we will maybe think of a better one, but for the moment, let's just do void memory region or memory. Okay, let's just call this fs memory, and we can create a constant here. So const expression int fat files. Okay, fat minimum memory, and we will think of a number here. Okay, required. Okay, I think that should be okay for the moment. So for the moment, what we want to do is to basically have enough memory to store this fat data structure that I have here. And what this fat data structure contains is basically the boot sector, the root directory. Okay, so and then we also had the list of opened files, and then the fat cache, and the list of long file name blocks. Yeah, okay, so okay, let's just have it this way. And then we will create a class here, fat data.hpp. And here is where we will have this fat data structure. Now, it might be a little bit different, but I think this is a reasonable approach. Yeah, now something here, Okay, let's create constants for sector size. We will not keep a list of opened files, although we still do have to keep this. Yeah, so the thing is, when we return one of these path files that we will return here inside this open function, when we return one of these files, we will need to refactoring means just improving the code design and everything. So just rewriting big parts of the code, fixing issues along the way. That's what refactoring means. You know, it's not an abstraction. It's just improving the code. That's what refactoring means. Yeah, but not just optimization. It's also about how you design all the classes and how you arrange all the files and that kind of stuff. That's what it means. Yeah. Okay. So we're still gonna have... We are still gonna need this list of open files, unfortunately. Okay, so let's see, what value did this have? Actually, let's just copy these. And we can make them const expressions now. Okay, max file handles, and we will just have a number. Now, obviously for the kernel this is not enough, but for the bootloader it's gonna be fine. Root directory handle. All right. And this one, where is it? Okay, there it is. Okay. Yeah, and inside the fat file system, now let's just add this memory stuff here. And what we're gonna do is we're gonna create a fat data section here. And this will be a pointer to the data. And then we will also want to have There were also another these here. Okay. So now let's go to initialize. All right, and here we have initialized the device, but we also need to initialize the other fields. All right, so data will just be reinterpret cost of to whatever type is this, so fat data pointer of that fs memory. Then the data section LBA, this will have to be calculated, so for now we can just leave it. Fat type as well. Oh, and these should not be G underscore. G is for global variables. Okay, and then total sectors and sectors per fat. And these are also going to be initialized in the initialized method, so okay. And now let's see. So we need to read the boot sector. We're gonna create a private function for that. Okay, and to read the boot sector, yeah, I'm just gonna copy the code from here because it's easier. Oh, okay, so here we had this partition stuff, but that's not gonna be necessary anymore. So all we have to do here is just go to mDevice and call read. Data is going to be, yeah, these boot sector bytes, and the size is gonna be just the sector size. And that's basically it. Okay, and that is how you read the boot sector. Hello. And we don't even need to pass the disk anymore. We just need to call read boot sector. Okay, and the module is that. Okay, let's just use define here. I'm gonna use a define log module, and let's just say fact. Okay, so if this fails, we will print an error message using that debug method. And then let's do the rest of the stuff. I'm just gonna copy everything. Okay, but we have to change a few things, so instead of G underscore, it's gonna be M underscore everywhere. And what? Okay, that's, I did not mean to do that. All right. Okay, so this is okay. This is looking good. Okay, then we need this cluster to LBA method. So let's add this one as well. Ah, I'm lost. Okay, so we need this cluster to LBA function. Okay, then what else? Okay, let's include fat headers. So include. All right. Wait, where is that directory entry? Oh, so it was in fat.h. That's why it's not there. Okay, I'm gonna add those as well. Yeah, so let's add those to fat headers. Okay, I'm just gonna put them here at the top. And of course, get rid of the type def. Okay. So this is looking good. We need that sector size here, so I'm just gonna move it from fat data into fat headers because we also need it here. And now we are error free in this file as well. Great. Yeah, so here this is gonna be, fat headers. It's looking good. And no more error. Great. Yeah, most of the stuff looks fine. Yeah, and then when instead of partition read sectors, we just use the disk function. Or the block device function. mdevice read, and then the data is inside that. It's this parameter here. And the size is just sector size. That's it. Oh, and okay, that's gonna be a bit of an issue because so here we are reading a specific sector. We are reading the sector from this LBA. So what we have to do instead is seek and then read that sector. So it might be a good idea to implement this as a function here. Read sector, and let's just pass in the LBA. And we also need a pointer to where to write data. Okay, now this is a very simple method. Yeah, so we can just use this. And yeah, I've noticed that read doesn't return a boolean, it returns the number of bytes read. So what we can do is check that the number of bytes returned is the same. So return this is equal to sector size. And this should... Okay, so it's expecting uint 8. Let's just put uint 8 then. Okay, so that is read sector. And now for read boot sector, all we have to do is just call read sector of 0. And that's where we want to place it. And we want to read sector 0 basically. Okay, and inside read sector, this is what we need to do. We need to call device seek, and the position would be LBA multiplied by sector size and relative to the beginning. Okay. Okay, the arguments are reversed. That's the error. Okay, so in order to read a specific sector, we need to seek, and then we need to read that sector, which makes sense. Okay, you want to get rid of the background music? Sure, no problem. I can stop it if it's that disturbing. There you go. Okay, so now what we can do is read sector using this read sector function instead. So read sector root dir LBA, and then we will place it here. And we don't need to specify the size, we don't need to specify anything else. Okay. All right, so yeah, you're welcome. Detect fat type, that's another one method that we need to implement. Yeah, so refactoring, it's just kind of rewriting this code. And it kind of gets tedious, and you think about a lot the architecture, how you design things. It kind of... And the idea is to make things as reusable as possible and as well designed as possible. And yeah, one of the major changes that we have here, which is going to benefit us a lot, is having this system with block devices. These device types are gonna be very are gonna be great. They're gonna be very easy to do a lot of stuff that would otherwise be pretty difficult. For example, having memory mapped files, so having like memory mapped file systems. That's also something we will be able to do. Having like file systems that are just stored in memory but not on the disk, or not on an actual disk, and a lot of other cool stuff like that. All right. Yep, this is the detection function. Okay, we can just make it void. Okay, back to initialize. Okay, now we want to call this function instead. And I think we are done with initialization. Yay! Okay, we are done with initializing stuff. Okay, now let's implement open. Parent doesn't make sense. We just want the actual file entry here. And let's see, where is our open function? So this is the open entry function, which does exactly what this opening. But here's where things are gonna be different. Okay, same as before, we try to find an empty file handle inside this list of opened files, because we will... Okay. Okay, if we are out of handles, we return a null pointer. In fact, wait, what? Yeah, so I found a little mistake here. So this function returns a fat file, but here I just returned false, and GCC didn't complain at all, so that's great. Okay, so yeah, instead of having this file data, what I'm gonna do is just have the fat file class have all of these fields, and we will have to initialize it. Okay, what else do we have here? So we are reading... Okay, so here we are reading the first sector from the file and putting it into the buffer. Okay, so let's see, how do we implement this fat file class? Because this is where a lot of this stuff is gonna be. Pragma once class fat file, which just inherits from file. And for that, we need to include file.hpp. Now, currently this file class doesn't have anything. It's just implements block device, but we will have to add a couple of things here. So previously I had this file data structure, which looks like this. So instead, all of this stuff is going to be inside that file. Okay, this public is not necessary anymore because this is how we kind of had like a public interface. We don't need to do that anymore, so I can remove that. And yeah, let's just add an m underscore so that we know that these are members. Okay, so now let's see. That file, when we initialize this, we will need what we will need. I think we will need to probably have a pointer to that file system itself, or maybe to some data from over here. Yeah, so let's think about this for a minute. What we're gonna have here inside that file system open, yes, we will try to find an empty file handle. So basically a file which is not opened. And these opened files here we're just going to use that file instead. So include that file.hpp, and instead of file data, it's going to be just like a normal file. Okay, and yeah, we don't have all the functions implemented. Okay, we will take care of that. We cannot have any arguments here in the constructor because we are initializing them inside this fat data structure. So we're just not gonna have anything in the constructor, but we will need an initialize function here. So void initialize, and we will need to pass some data from the fat file system class. We will think about what we actually need to pass in just a moment. And we will also want to have an open function. So bool open, and then we are gonna get one of those headers. So fs fat file. Okay, we have a conflict or not? I think we do, because we also have this fat file class here. So we need to figure out how to name these. Okay, so I'm just gonna call this. Actually, this is no longer necessary. This class I used to kind of for the public part, so this is not gonna be necessary anymore. But what is gonna be necessary is this pet directory entry. So in order to open a file, we need to pass a pet directory entry. Okay, and maybe, okay, that's not a bad idea to just not have initialize anymore and just put everything inside this open function. I think that's a pretty good idea. Okay. All right, and now let's see. So this opened is no longer accessible. So let's create a bool is opened. We will create a getter for this, and we can make it const as well. Okay, if that file is opened, which is now a function. So if this is not opened, then we have found a fat file class which we can use because we're just gonna reuse them. All right, and then and then we need to set up all of these variables. Now, what I'm thinking here is to just pass all of these in that open function. Okay, so what I'm doing here is I'm basically setting hold on a second. Okay, so I'm basically initializing all the fields inside this, which is probably not going to be necessary. Yeah, so we need to move all of these to fat headers to fat file .cpp. And yeah, let's create this open function here. And I've lost the clipboard, so let me get it back. What did I do? Oh, I copied the whole file. Alright, that's not what I meant to do. Okay, so what we'll have here extra is this. Okay, we will have extra this file handle. We will need it here. In fact, I don't think we need it. We don't need the handle. And let me show you why. So previously I used the handle to identify which whenever I called, for example, I don't know, fat read, for example. If I call fat read, then I have this fat file as a parameter. And I wanted to have the handle, so I knew which one of the opened files it was. But really I don't think this matters anymore. Yep, that is correct. Because now we can just use the address and search for the address. I think that's easier. Okay, what else is necessary? Is directory. Do we need to know this information here? Probably not. Or, So the basic idea is that the file entry will contain all this metadata about the file itself. like whether it is, the file name, whether it's a directory or a file, whether the file entry is going to contain all that information. And here, this is just going to contain information required for actually reading the file. This is like the opened file. So yeah, directory is not necessary. What is necessary is the position and the size. So let's add those here. All right. So position, size, and then that buffer, whether it's opened or not, the first cluster, the current cluster, and so on. Okay, and now we need to initialize these fields. Okay, I haven't included that file.hpp here. Okay, we are saving the size from the directory entry and also the cluster number. That's also something we need. Okay, so this is looking pretty good. Okay, so yeah, when we initialize the file, we want to start from the beginning. This is the size. This is the first cluster, and then the current cluster, and the current sector in cluster, because we are reading sector by sector, because our buffer is only one sector large. Okay, so this is what we open does, so we don't need to do this anymore. Okay, we can just call open, and now we need a fat directory entry. And that one should be basically inside this file entry here. Okay. Yeah, we don't have dynamic cost, so we just have to use static cost, I think. In fact, that might not work properly. Yeah, so we cannot open any arbitrary file entry. We need to open an actual fat file entry. That's something that we should change here. Or not. Okay, this is gonna be... Yeah, since we don't have dynamic cost, then this might actually cause some issues. Because what dynamic cost does is, so if you want to downcast, for example, we have the file entry, which is the base class, and you want to cast to the a class derived from file entry, like fat file entry, then you want to use dynamic cost because the address might be different. But yeah, the address will be different using pointers everywhere. Yeah, we don't have a choice because we don't have smart pointers and we don't have dynamic cost. We don't have a lot of things at the moment. And I was thinking about how to do this downcast properly. Now, if this file entry, so if this fat file entry had multiple inheritance, then this casting this using something like reinterpret cost will not work properly. Using references, okay, yeah, maybe it might make sense. You're not wrong, but There are a lot of cases where we also want to have null as a valid value, but you're right. Using references might help. Okay, so here I'm gonna do the ugly thing, and I'm just gonna cast this file entry to a fat file entry. But this might cause issues. If fat file entry has multiple inheritance, then this might cause issues. Okay, and let's just define a class here so the compiler doesn't complain anymore. Did I not declare file entry? Yeah, coding like it's 1991. Well, we do use a couple of newer things like constant expressions and null pointer, so it's not quite that old. Okay, so what do I want to do here? Because I forgot. Oh, right, so wait, where is this file entry structure coming from? Oh, it's coming from filesystem.h. Okay. In that case, let's move it to its own little class, its own little file, because that might actually make more sense. File entry .hpp. And for the moment, we are just gonna keep it like this. Oh, you need the file type. And now we need to include this file entry here to avoid errors. Okay, and now for the fat file entry, we will see what we include there later. But the idea, okay, not later. We will do this right now. So it should basically contain a pointer to a fat directory entry. This fat file entry. Using STL in a OS code. Yes, absolutely, you can use it. Now, my recommended way of using the STL in an operating system would be to embed one of these libraries, like embedded template library. I was thinking about trying to integrate something like this, but obviously you need memory allocation. That's one of the most basic things that you need for this to work. But yeah, it's a great little project which can be used to basically have like a sort of template library in your own operating system. Yeah, you don't want to use the standard library because in that case you're not compiling properly, basically. You might get a lot of issues trying to include things from the standard library, so it's best to avoid it at all costs. So don't use std c++ lib or whatever, just embed one of these libraries like the one I mentioned. And yeah, I mean, for me, implementing stuff like vectors and lists is not fun. I would rather work on memory management or something else. All right, so this fat file entry, it needs to contain this fat directory entry. In fact, it doesn't even need to be a pointer. It can just be an instance. And for the moment, let's just make it public. So directory entry. So something I'm not super happy with is that it's not very clear what is coming from the file system and which classes are from like the FAT implementation. Yeah. Don't overcomplicate things. I agree. I kind of tend to do that sometimes. Okay, so in that case here we can just take a fat file entry, or whatever, and we need the fat file entry.hpp for that, and in open this is just gonna be okay. We need to change the data type. File entry.dir entry, something like that. File entry dir entry.size. Okay, I think this is good. I don't know why it's giving me these errors. Incomplete type. What? Identifier loss undefined. Did I do something wrong? Oh, the file wasn't saved. I think that's the issue. Still. What the hell are you doing here? So yeah, this looks like VS Code issue. Because I'm pretty sure it says class here and not las. Oh, come on. And I don't think I have like any missing, I don't know, any extra character or something that would make it break like that. It's just weird. Yeah. It's just weird. Anyway, so let's continue. Right, where were we? So yeah, now it's fixed that I reopened the files. Great. Okay, so yeah, now this root directory, this will not work for the root directory, and we will need to change things a little bit. So we need to create like fat file entry, root entry, and we will set all of these parameters on the root entry. The name doesn't matter, the type doesn't matter, so just the stuff inside the dir entry. We're interested in the first cluster. Okay, so the first cluster low is what, 16-bit? Okay, that's gonna be a bit annoying. Root dir lba. Sorry. Okay, position and size should not matter. Okay, we need the size. Which is that number. Then opened is gonna be initialized by the fat file class, and then first cluster we've already set it. Current cluster, okay, we don't need these anymore. Okay, and what we need to do is just call the open method using this root entry. A GCC bug. Yeah, that's not cool. That sounds not fun. Okay, so... Okay, we don't need to read this sector anymore. I mean, we don't need to do this here. We can just do... We should do this inside this class here, so... right. We will see in just a moment. Then... Yeah, we call the detect fat type. Okay, but why do we do this here? That's curious. After setting up this root entry. I think we can do this earlier. Like here. Okay. And then reset all the opened files. So... Okay, we just need to call the constructors. Okay, so mdata. The thing is that this fat data isn't properly initialized like a normal C++ class would be. This is just reinterpreted from a memory pointer. And this is why I'm kind of thinking about how to properly initialize these objects, because this is a C++ object. And yeah, it's not gonna let us... actually, I think I can just do this. Fat file. Okay, so it's complaining about... yeah, we have a couple of functions that we need to implement in fat file for this to work, but other than that, I think we are good to go here. Yes, looking pretty good. Okay, open. So open, we just need to call that open function. We don't need to do any of this anymore. Okay, and then in the open method, we basically read the first cluster of the file. And okay, that's something that's a bit different. Okay, I'm going to remove this because we no longer need to... Okay, and then we just return that file. Okay, so basically this is what we need to do here inside the open method. We have this pool of files, we go through the list, try to find one which isn't opened, and then we just call the open function. That's it. So this one, it looks pretty easy. Okay. Now, we will need to pass some data to this fat file class because for reading stuff, for example, it also needs this read sector function. Okay. Yeah, I tend to have a more than 1.5 hour stream. Yeah, I tend to have very long live streams. I don't know why. I wonder that as well. Why am I doing live streams so long? Okay, so I don't know if I've explained how this works very well. I mean, at this point, I'm just moving stuff from one place to another. Yeah. Okay, let's implement this fat file class. I think this would be a good time to implement this. Oh, and yeah, what we didn't do yet inside fat file system is we didn't implement this get next file entry function. So this one should be okay. Let's do this first, and then we will go to fat file, and then we will go to fat file entry and implement those as well. Get next file entry. Okay, let me just open this back to see how I did things here. Actually, just to copy the code. Okay, so in order to get the next entry, oh yeah, we just need to implement this read entry function that we had here. So what I'm gonna do is, where is it? So I have this read entry. Yep, this is the one. Just need to add this to fat file, and then we can pretend that files can be directories and read them as directories. And that's it. Okay, let's see. I'm gonna paste this code here. We don't need these anymore. And yeah, we are just gonna read a fat directory entry. And we're gonna return a boolean whether it succeeded or not. Okay, now for the implementation, it's just gonna be like this. Okay, so read data is inside this dir entry, and the size is the size of a fat directory entry, and that's it. And yeah, we have to reinterpret cast this to a uint8. And that's it. So that is the read file entry function. And now let's go to fat file system, get next file entry. Okay, let's think about this for a minute. Okay, so what I think we need to do is change instead of file entry to actually be a file. So what this means is that we are basically reading the next file entry from a directory, from an opened directory, and that's what we should do here. All right. Okay, now we need a file entry. Okay, so what we're gonna do here is, hey, I just wanted to say that I've been watching your OS series and it is so helpful. You explain everything so well that even I can understand it. Yeah, you're welcome. I appreciate your response. Yeah, this refactoring is taking a lot of time. That is clear. Yeah, it is. I did not expect this to take this long, but yeah. Yeah, there's a lot of stuff that you need to think about. Now, so to get the next file entry, what I can do here is, yeah, this is gonna be a little bit annoying because if we do something like this, for example, I can read a static file entry something, and then I just set all the variables here, and then I return this file entry or whatever. Then the user is going to pass this file entry, it's gonna pass it to me, which is not gonna be, and if I make any changes to it, then this will also change. So maybe there's a better way of doing this. Okay, yes, let's just not have a pointer. Let's just return an object. So this would be a const pointer, and we will return an object because file entry, it's basically a structure. I don't really like the fact that it has this long name here, but that's the best we can do. Oh, and yeah, that's another issue here is that we cannot do this. And the reason we cannot do this is because we are basically returning a derived version of file entry, and we cannot have just a simple object. Yeah, I should write the basic allocator. I agree. I think that's kind of what's holding a lot of this stuff back. And all right. Let's write an allocator then. Yeah, let's write an allocator. This is kind of something that we will want to okay, let's do this. So inside this core library, let's go to, let's create a new folder called mem or memory or whatever. Let's, mem, it's fine. And let's create a class called allocator.hpp. And this is also going to be an interface. So I'm using Fedora. Okay, and all we need here for an allocator is just allocate and free. So, okay, void allocate, and we will just return a, okay, we need the size, so size t size, and void free. and we need to get that pointer. So this is basically what an allocator needs to have. Okay, we probably need std_def.h for size t. And we need to make this virtual. Okay, and now let's go ahead. In stage 2, I'm going to create a memory folder here as well. And let's create stage 2 allocator.hpp. Okay, yeah, something I was thinking about this stage 2 allocator is that there's something we actually need here in stage 2, which is kind of unique to stage 2. There are situations where we want to allocate stuff in the first megabyte. Whenever we want to interact with, for example, fat, then we absolutely need to get something in the first megabyte. If we are allocating stuff for, I don't know, maybe double buffering or something that will not need to be used from 16-bit real mode code, then we will not need that. So there are differences there as well. Okay. Core mem allocator.hpp. Okay, so let's implement these methods inside our stage 2 allocator. Okay, and we will also need to initialize it, and we need to know for the base and the limit, basically. So 2 numbers we need to know. How much? Okay, so let's just start with base address, so where we can start allocating stuff, and then where we can end, where the upper limit is. So uint32 limit. Okay, and let's make these public. Okay. And yeah, for uint32 we will need std int.h. Now, our strategy for allocating memory will be very simple. In stage 2, we will not be able to deallocate. And that's the simplest strategy we can have. And still have some sort of dynamic memory. Okay, so include stage 2 allocator.hpp. Okay, we will need to initialize 2 pointers here. And in fact, let's just have a uint8 pointer because as the base. And we will initialize these. Okay. Now, in order to allocate memory, what we can do is I'm just doing a very rudimentary memory allocation because I kind of need it for this file system, and it's kind of really not helping that I'm not able to do this. Okay, so we need to reinterpret this to a new int 8 pointer because it comes in as a void pointer. And now something has happened. What has happened? Oh, that. Okay, and in order to allocate, we're gonna have a very, very simple strategy. We are just gonna increment the base, and that's it. There's no going back here. If you allocate something, you will not be able to free it. Easy, right? Yeah, let's see how this will work. So, okay, we want to return the base, and then we will increment the base by size. And let's also check that we have enough space. So if size is smaller than okay, so base plus size is okay, we need the initial base. That's something we need here to keep track of how much we've allocated. Or we can just say how much we've allocated. Okay, so if allocated plus size is greater or equal to the limit, then we're just going to return a null pointer. Otherwise, we are going to return the base address. We are going to increment by the size, and then we are going to also increment the allocated by size. Okay, we don't have to even increment base at all. We can just set return equals to base plus allocated, and that's it. And then we increment allocated and return red. And that's it. We have a very basic allocator. All your base are belong to us. Oh yeah. Now free is basically gonna be an now op, so which means it doesn't do anything. So this is just a very, very simple rudimentary allocator. It will quickly run out of memory if we are not careful. So we kind of need to be careful and how to manage this memory. No, it will not work with new and delete. In order for it to work with new and delete, we need to implement a couple of functions. So let's do that. CPP. Actually, yeah, okay. New delete dot hpp. And we will need to include mem allocate not allocator. Stage 2 alloc. Stage 2, no. We don't even need this. Okay, stage 2 allocator. Yeah, that's right. But we will need to new and delete could be references to the function. Hold on a second. OS dev C++. There was a section here which mentioned how to implement new and delete. Yeah, so they're basically these four. And yeah, malloc and free. But the thing is, these are not going to give us the instance to this stage 2 allocator. So we kind of need to create like a global variable or something like that for it to work. But what we can do is just have like a global variable here. So yeah, let's copy this code here. What is the problem? Operator new of size T, and for some reason it's complaining. That's weird. Anyway, so yeah, we will need an allocator. So let's include the one from the library. So core mem allocator. CPP allocator. I'm gonna call it that, and it's gonna have a global function to set this. So void set CPP allocator equals this allocator. Okay, this will be initially null. So if CPP allocator is null, then we just return null pointer, and we will return CPP allocator allocate of size. What else? Come on. Function is inaccessible. Did I forget to make it public? Yes, I did. Okay, new delete. Okay, so yep, that looks pretty good. Same here. And for free, yeah, same here. I mean, it's free. Delete doesn't even return anything, so we can just call free of p, and then okay. So if this is not null, let's just make sure that don't cause any issues. I don't know why it's complaining. I don't have malloc here, but for some reason, it's complaining. Yeah, whatever. I don't care about it's complaining. Anyway, so now let's go to main. And I'm going to create an allocator basically here and initialize it right here, right before the start. So okay, let's just include stage2 allocator.hpp, and we are going to initialize it. And let's see if it's gonna let us construct this global object like this. Okay, so we need to give it a base and a limit. We had this memdefs.h. So the minimum is address 500, but I think... Hold on a second. Didn't I put this at address 500? Yes, I did. Of course I did. So yeah, we cannot use starting from address 100, but I think 200,000 is a pretty safe place to start. So I'm just gonna give it that. The constructors and destructors section. Hold on, let me see. Yeah, I already did. I already have that in this core library. under, where is it? I'm pretty sure I have it, but I can't see it right now. No, it's probably here. I had it. Then, okay, oh, okay, here it is. CRTI, CRTN. These are the ones. Yeah, it's right here. I have it. Okay, so memory minimum, memory max. Let's just set this to, I don't know, 200,000. That looks like a pretty safe place to start. And we don't need these anymore. Oh, this is wrong. Oh my god. Because stage 2 is not at 200,000 anymore. It's... yeah, I don't know. Okay, let's just use memory min and memory max to initialize this. So include memdefs.h memory min and memory max minus memory min. This looks pretty good. And yeah, we need to cast this to a void pointer. All right, and now we should have new and delete. A very rudimentary new and delete, but we should have new and delete. All right. Yeah. So now let's go back to this file system right here. Okay. So to get the next file entry, yeah, we can just allocate using new right now, but I don't know. This just doesn't seem like a very good idea to me because, I mean, we have that rudimentary allocator. It's very rudimentary and it's not gonna free anything. So we are just gonna leak a lot of memory, and yeah, if we need to search for a lot of files, then we will just fill up the entire memory. So I don't know. That doesn't seem like a very good idea to me. But yeah, using that, I don't have to do this anymore because now I can just allocate this fat data. So that is a big advantage, not having to do this ugly trick that I used to. Now we just allocate what we need to. And okay, yeah, and now that we have initialized this fit data properly, then this might also be initialized properly. I can cheat. How? Yeah, so what I'm thinking is to maybe allocate like a pool of these file entries, or another option would be to just have like inside the actual file entry class to have like a handle, and I would just read that handle and have like a pool of file entries. Taking a snapshot of where your allocator is and clear all allocations at once. I don't know about that. Yeah. I mean, sure, you can do that. Yeah, that's not a bad idea. That's not a bad idea, Alexandress. Alexandress. To take a snapshot. Yeah. Yeah, that's a great idea. So what I would do is to basically search for the file, and whenever I find it, I just delete all the allocations. But yeah, that could create issues. If any of those pointers remains anywhere, then it's gonna be deleted memory. So that's kind of what I'm thinking about. All right, get the next file entry. So this approach is a bit of a problematic. So yeah, you need to be very careful with that. Let's think about how to do this properly, how to get the file entries without having to allocate a lot of memory. Because even my idea would be to create like a pool of file entries and then just go through the pool. But yeah, that just complicates things. It's just gonna complicate things like it does with this file. I don't want to have to do the same thing for file entry. So what I'm thinking is, okay, so okay, let's let me think. How can we return this object here? File entry. So file entry is basically this structure here. And we want to return it. Okay, so one option would be to just do whatever I did in C. To have a reference to some object, or to have the object be allocated by the caller, and then just fill it here. Yeah, and then I would have to just not have that's probably the best option. And okay, the problem is that we kind of want to get the data. We want to... So we want to store some additional data. In addition to this name and this type, we also want to store this fat directory entry. A quick and dirty way of doing this would be to just have like a storage area here. It's kind of like a dirty, so just have like a new int 8 fs data and just allocate like, I don't know, 128 or 256 bytes. And that should cover however big this how big is it? Let's see. It was 32 bytes, I remember. Yeah. So a file directory entry is 32 bytes. So this file system data should be just plenty. I think this is just the easiest way of dealing with this. Yeah. Because otherwise we just complicate things a lot, and yeah, without having new, it's kind of impossible to return this. The other option would be to have because we want to return the derived object. We want to have the additional data there. And yeah, this is just the easiest way of doing that. Yeah, and what I can do is just have the fat file entry not have any additional fields here. That might work, but it's kind of ugly. Tagged union. What does that mean? A tagged union. A variant. Okay, so kind of like that. Yeah, but my idea was to have something like a the idea was to have to not have the dependency. I mean, everything here to just add on top of what is here. I don't want this I don't know, file entry to depend on the fat file. That's kind of what I want to avoid. And this is why I'm thinking about this solution here. It's just a dirty solution. I don't like it very much. I would prefer to do it the right way, but I don't think there's any other way of doing this. Yeah, so the option would be to just use new and return a new file entry, or to have a pool. Those are the two options. Or we could just, I don't know if C++ has that, but I think Java has. So if I return a more specific, I can do this, fat file entry. Although, a block list allocator. Yeah, okay, that's just getting complicated, and I kind of want to avoid complications. Okay, so I'm just gonna go with this solution for the moment. I can't think of anything better right now, so I'm just gonna go with this. So the name, the file system data, and then the type. And whenever we want to have a block list allocator. Okay, you're making me do things that I did not want to do. But you're right. Having a proper allocator is the best idea. Yeah, so creating like a linked list of blocks, and then yeah, that's probably the best solution. But yeah, let's not complicate things too much. I'm just gonna I'm gonna go with this. So I'm having this file system data. So the file system can store here whatever it needs to. Yeah, maybe later after I do the memory management, maybe I will have a proper allocator. But right now I kind of don't want to get too deep into that subject. I just want to get this done. All right. So what other options do we have here? So okay, let's just go for this. And this will be a reference, a constant reference, and we will just return a file entry object. Okay, and we will also need to modify it inside the file system class. Not that one, this one. Okay. Okay. And now we are just gonna fill up this file entry and then return it. But yeah, that's gonna make a couple of things not work very well. Yeah, I will get some errors here in... yeah, because it's not gonna be a fat file entry anymore, it's just gonna be a file entry, and we're just gonna have to cast that data, basically. I don't like this, but yeah, let's just keep moving. Let's finish this. Okay. So, in order to read the next... Okay, so in order to read the next file entry, all we need to do is just create this file entry and then call... so we know that this... Huh. I'm thinking about something here. Why am I doing this here? Why am I doing this get next file entry here inside the file system, when I could do it inside the fat file class? Yeah, I think that's a good idea. So the way this would work is we have the root file, which would be... Okay, let's create a function to get the root file. So, and I will move this to the file class. I think that's a better place for it. Okay, so virtual file root file. Our root directory. Let's just call it that, root directory. And I will move this to the file class because it kind of makes more sense for it to be here. So here we will have all the read, write, and everything else we have inherited. And also we will have this get next file entry. And we already know that we are the parent. Okay, I will add this to the file class, and we will just have the implementation here in fatfile.hpp. Okay, let's see. So yeah, now I'm gonna delete this and let's add this root directory function. And yeah, this is the first thing that I did here, was to open the root directory. So we can just return it. That's it. All right, now let's go into fat file. So what we have to do here is implement all the functions. These. Okay, now I'm just copying and pasting all of them. And also these. Okay. Open will work with one of those file entries. No option. We have no choice there. So I'm just gonna delete this class because it doesn't make any more sense. And we're gonna use the fetch directory entry as the data. Okay, so let's start with the constructor. Okay, and we have all of these things to initialize. The most important is just the opened one. We're gonna mark it as not opened. And then the rest, I think we just need to initialize with the default. Okay. Then open. So open will take a file entry reference and what are you complaining about? File entry is undefined. Okay, let's define it. All right. File entry dot file system data. Basically, that should give us the data itself. And yeah, we need to cast this using reinterpret cast to fetch directory entry. Oh, okay, so it should be a const. Okay, and this is looking good. Dir entry size, dir entry first cluster low, and dir entry first cluster high. All right. Okay, I will also need this read sector function. And yeah, we will need to pass some of this data here. Okay. Yeah, so why did I decide to move to C++? A couple of reasons. First of all, I don't like C. It's because C++ has a lot more features. It has a lot more abstractions. It has classes, it has namespaces, it has inheritance, and a lot of extra features that you don't have in C. And when building an operating system, you have to deal with these abstractions. You have to implement them. And okay, let me show you something. Let me show you how Linux does abstractions. So Linux, source, I don't know, let's see, for example, the driver for the PIC. That's something that I've, PIC driver. In fact, it wasn't called PIC, it was called the A259. Hold on a second. PIC 8259. 8259. Okay, here we go. This is something I've looked at recently. For example, here we go. So in order to create like a class, you basically create the base structure, and then in the derived classes, the so-called derived classes, for example, this i82598 chip is an IRQ chip, and you basically need to set all the fields, and all of these are function pointers. Except for the name, all of these are function pointers. And that's just to define a class. It's very ugly. I personally don't like it. The fact that you don't have all of these abstractions. And yeah, there are some concerns that people had about performance. Performance is not a problem, believe me, because doing the same thing in C manually, or doing the same thing in C++, but you have that as a feature provided by the compiler, maybe the compiler will know better how to optimize that feature, for example. So I don't think that performance is there's going to be a big impact in performance. Now, obviously, if you used a lot of abstractions, then you will lose some performance there, but yeah, being able to reuse code and having an operating system which is very flexible and allows you to do a lot of things that this allows you to do. In terms of operating system design, I think C++ is much better. So that's why I am using C++. Okay. Yeah, now read sector. Yeah, so I need to... I have this function here for reading a sector, and I will just need to copy it. Okay, so I'm just gonna copy this function for the moment, I think. Okay. The best option in this case would be to just okay, so read sector depends on this block device. So why not just pass the whole file system as a parameter to this fat file, because it's gonna need to use it anyway. So okay, and I'm gonna make this function public, and inside fat file open, I will also require that I get past the file system. All right, and let's save this here. Okay. And now I'm going to add it to the open method. Identifier fat file system is undefined. Okay, so I'm just gonna forward declare it here because I want to avoid having like a dependency issue here. All right, so here we can include file system fat file system.hpp. All right, and here we need to call read sector from the file system. Okay, and so what I'm doing here is for the okay, so when we open a file, Let me see the old implementation here. So I have this fat open entry. I'm basically reading the first sector and putting it into memory. Thank you. I look like a good streamer, very rare content, and it looks like I know stuff. Thank you very much. I appreciate your appreciation. Yeah. So what I was doing here is okay, I'm trying to think here. I only look like I know stuff. Yeah, well, what can you do? Everybody has to learn, right? All right, so okay, I'm thinking. So for the root sector, I have to use what I did here as the first cluster. Yeah, so the root sector behaves a bit differently, and here is also, let me show you the read function. Read, yeah. So, okay, so this is complicated. Let's see. Do I cover this case anywhere or not? Okay, so the way this works is that for the root directory, the root directory is weird. There are two basic ways of storing the root directory. As far as yeah, so if you are using FAT32, then the root directory will have a cluster number, which is this cluster number right here. So you can use like the first cluster. But if you are in my voice has left me. Wow, what the hell? Okay, so the way this works is like this. In FAT12 and FAT16, you basically have the file allocation table, and then the file allocation tables, and then you have the root directory, and it's gonna be big. This directory entry count is gonna give you how big it is. Yeah, one of the side effects, yeah. But if you are in FAT32, then FAT32 doesn't work that way. FAT32, you just have the file allocation tables, and then you have the data. So there's a little difference there. So yeah, depending on how... Okay, the way I basically have implemented this is that I don't even... Okay, so I have this first cluster here, which gives me the first cluster, but hold on a second, what am I doing here? Because this first cluster is not the cluster. All right, so in FAT32, we need to pretend that root directory is just a normal file. We just read it like a normal file. It will have okay, it has a, let me check because I don't want to be wrong about this. So FAT32. Root directory. Let's see where the root directory is mentioned. Yeah, so as I was saying, this root directory only exists in FAT12 and FAT16, this root directory region, like this reserved region. You're welcome. You're welcome, Emin. And okay, let me see. Where are you? So what I'm interested in is how it is in FAT32. Okay, so it typically starts from cluster number 2. Okay, that makes sense. But okay, and then we just use the file allocation table and we look at the cluster and we see which cluster is next. So yeah, in FAT32, the root directory behaves like a normal file, but in FAT16 and FAT12, it doesn't. It uses this it's basically a separate region right between the data section, right between these file allocation tables and the data region. So that's the difference between FAT12 and FAT16. Okay. Now, something here we need to keep in mind is how we read this. Okay, so let's see. Next cluster. Okay, this one is just giving the next cluster. Okay, this one looks fine. Okay, here. So if we are on the root directory handle, nothing. Okay. This might actually not work for FAT16 if the root directory is too large. That's weird. I think I might have a bug here because I don't see this case handled anywhere. So maybe I have a bug. I don't know. I could have. All right. So yeah. We need to handle things a bit differently if the file we are trying to open is basically the root directory or it's the a normal file. If we are in FAT32, then this will behave just like a normal file. But if we are in FAT12 and FAT16, then we need to treat it differently. All right. Yeah, we need to make a few things public here. We need the fat type. So let's just have uint 8 t fat type. And let's make this const. And we will probably need some other things. All right. Now, when we open a file, we have passed the what I think might be a good idea is to just create a separate function for this. So let's create a separate function for open root directory because it's a different implementation anyway. So let's just have a separate function for this. Yeah, and for the file entry, I don't think we even need it. Okay, let's not use it. Because there's no point. Okay. And now let's duplicate this function. The first one will be open a normal file, and this one will be open root directory, which doesn't have a file entry. Doesn't have a directory entry. And in fact, we can even go a step further and call this function open root directory fat 1216 or 1216. Okay. Just to make this clear that you can hear my Romanian accent. Oh no! I'm from Romania, so... And I don't speak English every day. Maybe if I spoke English more frequently, my accent would be better. Okay, yeah, so I will create a flag here. What are you doing again? This is really weird. I don't know. Maybe I'm pressing Control Shift S by accident, but no, it's open folder. It's something else. It's just an annoying issue with GNOME. Because it's not focusing on this window. It just appears behind, and input is not working. I don't know why. That's annoying. I hope they fix this bug. All right. So let's also add another flag here. Bool is root directory. All right, and if we are using FAT12 or FAT16, then the answer is that yes, this is a root directory. And if we are not, then no, it's not. All right, and we also need to initialize it in the constructor. One dark pro, I think, is my theme. Color theme, yeah. One dark pro darker. It's even darker. Okay, and this was the code for reading the root directory, the first sector of the root directory of FAT16 and FAT12. All right. And in that case, we can use the first cluster as basically where the data region begins. So just gonna reuse that. All right, where are you? So, okay, this is the open entry function, but yeah, okay, we need this. We will need this. And yeah, let's also not forget to set the opened flag. All right, fatfile.cpp. Okay, so we are preparing all these fields. We're not in the root directory of FAT16 or FAT12. The rest should be okay. And then we are going to read the next sector. And then we need to do this cluster to LBA conversion. Okay, what I can do here, just to make things a bit easier, is to create a function to convert read cluster read. Actually, since we're reading sector by sector, let's just read sector from cluster. And the first parameter will be the cluster and then sector offset. Okay, and for the implementation, we basically need to convert from a cluster to a exactly what I was doing here in this clusters to LBA function. So this uint 32 LBA equals the data section LBA plus the cluster minus 2 multiplied by, okay, yep, that looks good. And then LBA plus sector offset read return read sector of LB plus sector offset, and then just the buffer. And that should make things a little bit easier for us in file.cpp. So here, instead of reading sector, we just read sector from cluster, and we're gonna start with the first cluster, or whatever, the current cluster. Sector offset. Why is this set to 1? Another weird thing. Why did I set this to 1? Why am I reading? That's odd. Because I would expect to read the current sector from... Oh, 1 was the size. Yeah, that's why. 1 was the size. And then we read that into the buffer. So if this read fails, we just bail out. So print the error message, and that's it. Yeah, let's just not have the LBA. All right. Log module, fat file, and include core debug.hpp. All right. What am I doing here? Oh, printing the name. All right, printing the name of the file, but we don't have it, so... actually, no, we do have it. Hold on a second. Open file failed, and we can print the file name. So it's in the file entry dot name. Okay, nice. And then return false. All right, and if everything is gone all right, we will mark the file as opened. All right, now for that weird root directory. Yeah, so the size will be different. Yeah, let's expose this data section here. So add data. Turn m data. And we can even dereference it. Oh yeah. All right, so let's see. In the case of fat file system, this is where I'm looking. So right here, when we are initializing, yeah, so yeah, here we will need to open the file differently. So if the file is a FAT32, then we will need to open it. Yeah, we need to create one of these file entries and then mess with the data. So directory and fat directory entry. Reinterpret cost to a pointer of this of root entry dot file system data. That piece of data that I reallocated. All right, and then we need to update all of these fields. Oh, I already had this cluster to be function. I don't know what I'm doing here anymore. No, we don't have it. Okay, so I do need this function after all. All right. Okay, here we go. Cluster to LBA. And this one is doing the exact same thing. So cluster to LBA of cluster. Yep. I don't know if you've noticed, but I kind of have a very chaotic way of writing code. I remember something, I go there, and then I go back, and then I change something. When editing the videos for the main channel, for me, they're a nightmare because I kind of jump all over the place and kind of have to always keep that in mind when recording to okay, I'm not gonna jump. I'm not gonna jump. I'm not gonna jump all around. But yeah, it's hard. It's hard to resist. I'm really sorry about this. It's just how my mind works. Yeah, when editing the videos, it's a nightmare to try to put it together in a way that makes the most sense and is the most clear, and it's in logical steps. And then, okay, so I changed the thing here. Then how do I put that in the video? How do I integrate that? Yeah, it can be pretty hard sometimes. Okay, and now to open the root directory, we need to pass the file system and that file system entry, which would be this one. Okay. And we don't know this. Oh, do we know the size? I'm not sure if this is correct. This directory entry count. I'm not sure if this is correct. I have no idea. Let me check. I'm discovering things that are bugs. So, root directory size, where are you? I'm just going to go to OSDev because this one's simpler and I can read simpler. All right, so number of root directory entries must be set so that the root directory occupies entire sectors, but it's not mentioned anywhere. All right, so it was okay, the BIOS parameter block, exactly. Okay, so here it says that maximum number of FAT16 and FAT12 root directory entries, 0 for FAT32, where the root directory is stored in ordinary data clusters. Okay, but there is something we need to check. Okay, so this is where the root directory starts. Okay, so what this means is that we don't have a size. The size is basically theoretically infinite. Practically, you just have to go through the clusters and find where it ends. It's a bit unfortunate, but it's a bit annoying because we don't have a size. We don't have a proper size. Yeah, I was sure that this is probably wrong, so here you go. So the size, we cannot determine it right now, so we're just gonna set it to like infinite. We don't know the size, but we do know where it begins. So there's this first cluster and that gives us where it begins. Okay, and yeah, and then we can just open it like a normal file, and we are going to use the the file allocation table. We're going to use the file allocation table to go into the next entry until we reach the last one. Okay. For this other thing, okay, I'm also doing something wrong here, I think, because I should store the cluster itself. So let's just store the cluster itself, not the LBA, because that doesn't make any sense. And directory size, do I use this later anywhere? No, I don't. But I do need this data section LBA. All right, so I'm not using these values anywhere, so I can get rid of them. All right. Now, if we are in FAT12 or FAT16, then the root directory is gonna start at this LBA. And the size is going to be given by this number. And the size in sectors is also going to be given by this number. Okay, so what I think I'm going to do is I'm just going to put the root directory LBA and also the size as parameters here. I think that would probably be the easiest way. So uin32 root directory LBA, because we need to know where it begins, and we are also gonna get the size. So root in 32 root directory size. Okay. Okay, so now let's finish this. This is where it begins. This is the size, and this is the size in sectors. I don't think we care about the size in sectors. We just care about for calculating where the data section begins. All right, and now we're gonna do data root directory dot open root directory 1216. Using this file system and using this root directory LBA and using this root directory size. All right. Yay. And of course, if this operation fails, then we need to return an error. So if this fails, we are just gonna return false because we've printed a message here inside open. All right, so if this fails, then we just return false. All right, this looks good to me. So this is no longer necessary, this whole thing. And the opened files, I think these should be initialized. Or maybe not. I don't know. We'll see. But yeah, we just need to make sure they are properly initialized. And other than that, what other errors do we have? Here in the open, we also need to pass the file system, which would be this. And all right. Okay, for the moment, let's just pass this file entry as it is. And now, let's see. So open root directory 1216. Yeah, so we are going to use this root directory size. And we are going to use this root directory LBA instead of the first cluster. Okay, and yes, we are starting from 0. And yes, we want to read the first sector into the buffer. And this looks good. Hey, and now we have successfully opened the root directory. So let's go to the next method. All right. Yeah, this get next file entry that I was talking about earlier. Let's do this at the end. Seek. Yes, we didn't have seek previously. And now we will have seek. Yay. Does it show the number of errors? Oh, here. Yeah, it's pretty good. We're making progress. This is called progress. Getting rid of errors. All right. Okay, so in order to seek, this depends on that seek position. Okay, so switch position. If the position is the beginning, so seek pos set. Right. So if we are seeking from the beginning, then we will need to basically do everything we did in open. Yeah, so the easiest way to do this is just to reopen the file. Yeah, so we're just gonna open using our own file. Oh no, we don't have the file entry. Oh no. You know what? I don't need a file entry. All I need here is the first cluster and the size. So that's it. So why just pass this whole file entry here? Let's just pass what we need. This is gonna make the other stuff easier. Okay, so first cluster and size. That's it. That's all the information we need. With blackjack and hookers. Yes, we're gonna make our own file entry. That's the spirit. Yeah, so yeah, I will have to move this code to fat file system. Okay, and yeah, we need to get that directory entry from the file entry, file system data, and yeah, let's get the size and the first cluster. And now we can just open using first cluster and size. That's it. And this is also going to make things simpler for seeking from the beginning. Oh, and now I changed my mind. So the thing is, we want to go to the first cluster, but we also want to go. We don't want to read the first sector because reading the first sector would be just pointless. It would be just pointless. So let's find a better way of doing this. Yeah, so what we're gonna do is just reset the position. Okay, so we need to reset these two first. All right. And we need to basically obtain the next cluster. And for that, let's go into the fat.c. And where is it? Next cluster, here we go. So I'm gonna put this function in the fat file system. Though. All right, and we're gonna make it a member function, and we're gonna declare it here, and we're gonna make it public. And what else are we gonna do? We're gonna implement it, of course. How can we forget? All right, add cache size, sector size. All right, so we will take care of this in just a moment. All right, don't gdata me. Hookers where and how much? I don't know. Maybe you'll find them. At least in my country, you can find the hookers. You know, on the next to the exits from the city. You can find some there. And how much? I don't know. I never asked them. I wouldn't recommend them. Okay, and now we also need another read function. Plenty of them online, of course. You can always go online. Oh, you know where you can find them? You know, when you get those emails like hot hookers in your area, that's where you can find them. LBA offset. Okay, so read fat is gonna basically read in real life. Yeah, that's why you get those emails like hot something in your area. Contact them online. Yeah, you contact them online and then you meet and that kind of stuff. What was I doing here? Because I forgot. I got distracted. Yeah, so I was copying the read fat function. Where are you? Fat open. Open entry. Read fat. There we go. Right. All right. Read fat. Okay. Yeah, good to know, Alexandros, that you worked for some hookers. Yeah, you gotta do what you gotta do. Well, you gotta do what you gotta do to earn some money. Um, yeah. I've noticed something here that I kind of would like to fix this read sector function. I would like it to also be able to read multiple sectors. So I'm gonna add a count, which let's just set to 1 so we don't get errors everywhere. And instead of reading sector size, we read count multiplied by sector size. And that's it. Okay, and now we are going to read into the fat cache from the... Okay, the LB was first. Reserved sectors plus LBA offset or index, same thing. Fat cache size is the count and the buffer is the fat cache. All right. So now we have this read fat function, so we can do this. And now we should be able to get the next cluster. So given a cluster, we can find the next one. And this is what we have to do here inside this seek function. So, and yeah, let's set the position to 0 as well. And while the position is smaller than the desired position, which would be rel, we need to basically just go to the next cluster. Let me check something first. Inside fat read, I already have this logic implemented here in fat read. So fat read. Okay, there it is. So special handling for the root directory. Okay, calculate next cluster and sector to read. I don't know. Alexander's, I wouldn't really brag about that. I mean, I don't know. Kind of weird. But yeah, sure. Why not? All right, so I was thinking about how to do this. So what I'm thinking is that what we can... All right, so basically what we need to do is just okay, so let's start with the beginning. So if the difference is okay, so in fact, let's do another way. Let's see. While rel is greater than 0. So if rel is bigger than a cluster, so cluster size, where is that? So that would be in the file system dot data dot Cluster size. Where can I find that information? Yeah, so it's in the boot sector somewhere. Dot data dot boot sector dot boot sector dot cluster sectors per cluster. So okay. So if rel is greater than the number of sectors per cluster, so it's basically bigger than a cluster. Multiplied by the sector size, then we are gonna increment. Then yes, we are gonna go to the next sector, which was that logic in fat.c. Okay, so it's basically just this. This is all we have to do. It's not too much logic. So we basically go to the next cluster in the chain. Okay. Now something that I'm kind of thinking about here. So real men don't get lost in code. So you're telling me that I'm not a real man? That I get lost in code sometimes. Yeah. Yeah, when you have a big code base, yeah, documentation is pretty useful, but I agree. All right, so basically we have to repeat this logic for the current as well. So, but it's a bit more complicated than. All right. Yeah, if I'm thinking about all the possible cases here and how we could implement seek in all of those cases. Now, a couple of cases that are kind of what if rel is negative? In that case, this is gonna be a bit more complicated. Okay, so what I'm gonna do is I'm gonna implement this separately for set current and for end, and then wherever I see that code is repeating, then I'm just gonna try to fix that. All right, so here we are going to the beginning of the file, and then as long as relative is greater than 0, we basically read cluster by cluster and we try to get the next cluster from the chain. So get next cluster from the current cluster. Okay, so we reset from 0 and then we keep going. Okay, so yeah, if the current cluster. Okay, so if the amount of data we want to seek is greater than one cluster, then we advance by one cluster and read the next cluster. All right. And then we want to advance the position by this big number here. And we also want to decrement rel. So rel minus equals this. Yeah, I don't like repeating this long thing too many times. So let's create a variable for it, cluster size. All right, so if rel is greater than cluster size, we are gonna read the next cluster and we're gonna advance by one cluster. And the amount of data left to advance is also gonna, I'm gonna subtract cluster size from that. Okay, else if this rel is greater than sector, so it's greater than sector size, then we know that we need to increment the current sector in cluster equals rel divided by sector size. In fact, I think I can just do this without another if. So just else. In this case, we don't need to advance. So the current sector, so this would be the offset in the current cluster, is however many bytes are left divided by the sector size. And then the offset, the position will be rel modulo. So the remainder of this division, basically. All right, and then we can read the actual sector. So let's do that. Not using this method, but using this. Okay, I can rewrite this a little bit. So I calculate the cluster size, and while rel is greater than cluster size, then I do this. And this doesn't have to be inside the else, it can just be outside. And then we are going to read this sector from cluster so that we are set in the right position. And yeah, there's no error here. This just returns void, but I think seek should also be boolean, so let's fix that. And now I have to change it in a lot of places, which is annoying. I have to change it in block device, boolean, and I'll have to change it in other places as well. Here as well. Oh, and we don't need those breaks anymore. All right. I opened this dialog, didn't I? What is the key combination I keep hitting? Open folder, Control K, Control O. I don't believe that. I'm hitting Control K, Control O. That's weird. Yeah, so this one returns a boolean. Then what else do we have? So I don't know. I guess we'll see if we get any other errors when we try to compile this. But yeah, seek should absolutely return a boolean. All right, so all right, this looks good. And I can just say that seek failed. All right, and return false. And by default, we return true. All right. Actually, I think we can just return this. And let's just not print the error anymore. Why should we print the error? I think it's fine. All right. Okay. Now, if we are trying to seek from the beginning and the position is negative, then this doesn't make any sense. So it's just, I don't know. Is it gonna do anything? All right, let's add a check. So if rel is smaller than 0, then rel equals 0, because we don't want to mess up this position here. All right. Next we have current. So case seek pos current. Okay. Now, from the current position, we could either seek back or we could seek forward. Now, if we seek back, then we might have a problem. Because, okay, so let's see. I'll have to add another case here to add an if at the beginning. So if seek post, if we are trying to seek from the current position and how much data we... Okay, let's get the cluster size because that is a useful piece of information. We need it here. All right, so if we are trying to seek more than cluster size, so if and the rel is negative, this is also another condition. So if we are trying to seek back, but we go past the current cluster that we are at, then we need to read from the beginning because we don't have any history of the clusters. So we basically need to convert this seek call into a seek set, basically. All right, so if we are trying to seek from the current position, actually from... this also makes sense from the end. So this would also make sense when seeking from the end. No, this is fine. Okay, so if the position is current and rel is negative, and we basically need to go back. So the current position modulo cluster size. So what this will give us is the current position in the current cluster. So for example, if we are at cluster 10, this cluster size will be 10 multiplied by 1 kilobyte because there's usually 2 sectors per cluster. So each cluster will be 1 kilobyte, right? And if our current position is, I don't know, 1 kilobyte and 10 bytes, then this will give us the 10 bytes. All right, and if rel, so minus rel, in fact, because we want to get the absolute value. If minus rel is greater than this number, okay, so if we need to seek back more than the current cluster. That's what this do. And if that is the case, then we will convert this into a seek from the beginning. So pass equals seek pass set, and rel equals the current position, so m position plus the rel, which is a negative number, which means that it will subtract it from the position. So then we need to convert this to a seek from the beginning. Okay, does this make sense? I hope it does. All right. Okay, so if we need to seek back more than the current cluster, then we need to convert this to a seek from the beginning. All right, that makes sense. All right. So if we are seeking from the beginning, then we go through this logic. If we are seeking from the current position, then we kind of have the same logic here. So let me think about this for a minute. Okay, so if we are seeking from... yeah, so this logic here is gonna be common for both set and current, this logic here. And I think we can move it below this code here. Now we need to figure out how to... Okay, so for the current situation, same as we did. Okay, so we need to figure out whether we will cross into the next cluster or not. And if we will cross into the next cluster, then yeah, we need to go through this logic here. All right, so let's see. If okay, so let's get... I'm creating a scope here, and the reason is so that I can create a variable. Let's say left in current cluster equals position modulo cluster size, and then we need to subtract cluster size from this. So that will give us how many bytes are left in the current cluster. All right, and if left in current cluster is smaller than rel, then we advance rel by... okay, so we basically subtract okay, so we subtract from rel how much data is left in the current cluster, basically. And then we will go into this logic, which goes to the next cluster, while rel is greater than size of a cluster. Yeah, that looks pretty good to me. Okay, so let's see. If okay, let's add a break. Else, that means that we have to we have to seek less than the size of the current, what's left in the current cluster. So we just need to advance the position. We advance it by rel and set rel to 0. So because we no longer need to advance anymore, I mean, we can just return here. I think we can just return true. And we also need to modify the current sector in cluster in case we cross sector boundary. All right, so okay, so the current sector in cluster is the position, basically the position modulo okay, it's basically left in current cluster divided by the sector size. That will give us the current sector in cluster, and that's it. And we can exit. Okay. And then we go through this logic, which I already explained. Okay, and let's see the last case. If we are trying to seek from the end, again, we have the same situation. Okay, so if we are trying to seek from the end, then there are two possibilities. The first possibility is that we are just trying to get to the end of the file. I mean, I don't know why you would want to do that. I don't think you would want to do that. Because, I mean, usually seek post end is used to determine how big a file is. And I don't think we need to do that here because we have the size function. So the only use for end would be with a negative rel, with a negative position, and we are trying to basically read, like, I don't know, the last couple of bytes in the file. Yeah, and if that is the case, then all right, let's just cover it in this case as well. So yeah, if pos is seek pos end, then we just convert it to seek from the start, and the relative position will be the end, which would be size plus the rel, and that's it. Okay, a lot of complicated logic for all right, this looks kind of complicated. I think we could just get rid of the switch because it's not even used anymore. Okay. Seeking from the end, and we can't iterate backwards. We can't iterate clusters backwards, so we have to start from the beginning. All right. That just makes sense. All right. And then, yeah, so if pos is from the beginning, then we do this stuff. In fact, what I'm thinking is I can just... Alright, so... I don't think I even need to do this anymore. Okay, so I'm gonna modify the logic a little bit, so... Okay, and then we can put the rest under an else. So... which would be this code here. Okay, so hold on a second. Let me think about this. Left in current cluster is... I'm thinking about this so complicated. I think there's an easier way to do this. Which means to just change the position and then call a function which updates the current cluster. I think that might be a lot easier than what I'm trying to do here. I'm overthinking. Okay, so let's, I thought of an easier solution. So I'm gonna create a function to, let's just call this, navigate to, okay, let me think about it. So update current cluster. Okay, let's just call it on position changed. I think this makes more sense. Okay, update plus current cluster. And I'm gonna make this a boolean. And let's not overthink this problem, because I kind of overthinking and making a lot of complicated logic here, and I think we don't have to do that. So basically what I'm going to do is here I'm just going to set the current position, and that's it. So yeah, if we are seeking from the beginning, then we are going to change the current position to rel. But yeah, if rel is negative, then we need to handle that case as well. So if rel is negative, then position a equals 0. Otherwise, position equals rel. And let's just do a static cost here to make things between 32t. And that's it. If we are trying to seek from the current position, then what we need to do is just update the position. So again, same as before, we can check the boundaries to make sure that, so if position is, okay, so if rel is negative and minus rel is greater than position, then that means we should be at the beginning. Same. Okay, I'm overcomplicating things again. So position is a static cost of std max between 0 and rel. And I don't know. Okay, it's not in std. It is in algorithm. Or CPP algorithm. Hi. Welcome to my stream. Okay, there we go. That's easier. Okay, same as before. If we are seeking from the current position, then C++ sandwiches. Yes, I agree. Tasty. Yummy. All right, so now the problem here is that rel is signed and position is unsigned, because otherwise I would just do this and just check position, the boundaries of position. But because this is unsigned, then we might get into trouble if we do that. So yeah, I'll have the if. So if rel is negative and position is smaller than minus rel, then position equals 0. Otherwise, we're just gonna do position equals static cost of the minimum between the size and the current position plus rel. Yeah, and yeah, we need to cast this right here. All right, and I think this looks pretty good. And if we are trying to seek from the end, same, I will check this. So if the relative position is bigger than the size, then yeah, we're gonna set it to 0. And then position equals minimum between size and, okay, the position is, yeah, same as before. Yep, there we go. And now we are just gonna call that update function. So update current cluster. And in update current cluster, we basically have 3 cases. The case when we have to seek back, in which case we need to just do the logic from the beginning. the logic when we don't have to change anything, and the case when we have to advance. That's it. All right, so desired cluster equals position divided by the cluster size. So we need to calculate the cluster size again. I mean, not again, but just move the calculation here. So we want to be in this cluster here. So position divided by cluster size. Then we want to be desired sector will be the position modulo cluster size. So the remainder of the position divided by the cluster size divided by the sector size, and that's it. And now we check if we are there. So if the desired cluster is smaller than the current cluster, in that case, we need to go from the beginning. So current cluster equals 0. We go from the beginning. Okay, and if desired cluster is greater than the current cluster, which will be true if we change this as well. So we're not using else if. Yes. Then we need to go from the beginning to all the way to the current cluster. So let's go. Okay. Something I missed here is what I've calculated here is basically the index of the desired cluster, and this is the actual cluster on the disk. I don't have the current index saved anywhere, so I think it might be a good idea to save it as well, so we know where we are. So current cluster index. Let's save that as well. And we are... Okay, so the current cluster index is 0 and current cluster equals first cluster. Okay. Now, if the desired cluster is greater than the current cluster index, then we advance. So we advance, increase the index. Actually, we can make this a while. All right. And we increment the current cluster index. Okay, and now we have arrived at the right cluster. Next, we need to arrive at the right sector. Okay, there's an I was thinking about this. So if we are already at the sector that we want to be, then we can just exit this function. But after we modify the current cluster, then we won't know if we are at the desired sector or not. So basically what I have here, you can think of this as like a position having two numbers, right? So like an X and Y coordinate. The X is the desired cluster and the Y is the desired sector, basically, right? And if you change the X, then whatever data I have stored, even though Y is the same, then the data will not be valid, so that position will not be valid. But if we have the same position, so if desired cluster is equal to where we want to be, and also the sector is where we want to be, current sector in cluster. So if we are where we want to be, we just return. Okay. And then we go through this logic. So first we try to update the cluster. So we navigate to the right cluster, and then we need to navigate to the right sector. So I mean, there's nothing we need to change about. Okay, so all we need to do is just modify this current sector in cluster equals desired sector. And now we perform the read that we had here. So we perform the read, so we read the data for the current sector and cluster. Okay. And all of this is no longer necessary. And I think this logic makes a lot more sense and it's easier. Yeah, there we go. Instead of that hugely complicated seek function, now we've basically simplified it a lot. Yay, we have seek, but now we need to take care of this current cluster index. So let's take care of this one. Okay, current cluster index is 0. Yeah, that's basically it, because we haven't implemented the read yet. Next, we have the size function. Okay, this one is easy. I can just return size, and that's it. For the position, same. All right, and then we have read. The read is gonna be probably one of the most complex methods. Override. All right, fat file. I'm gonna put it here above seek. Okay, first let's start by copying the logic from here. So all right. Now, this works a bit differently now. We already have all the information we need, so we don't need to do this anymore. Data out. Okay, so previously data out was a void. Now it's uint8, so nothing we need to do here. Okay. Wait, hold on a second. What byte count? Where is byte count coming from? And why is it not here? Okay, so all right. It looks like directory entries can have the size 0, in which case it might be a good idea to try to figure out how big it is. Although I don't think it matters that much. Okay, so we need a new entry here. We need to figure out if this is a directory. So we will add that here. Is directory. Okay, so here I'm basically checking that the size given by the user doesn't go past the end of the file. Okay, so if this is not a directory, so if this is a file, or if this is a directory and the size is non-zero, which means we have a definite size, then we want to make sure that we don't go past the end of the file, in which case, yeah, byte count is the argument. That's it. All right. Okay. In this case, we basically verify that why is M position undefined? It's right here. That's weird. Okay, this is just VS Code acting up again. Alright, so while byte count is greater than 0, we try to figure out how much data is left in the current buffer, basically. Alright. Yeah. Yay, it finally fixed itself or whatever. Yeah. So, yeah, special handling for the root directory. If this is the FAT12 or the FAT16 root directory, then we just increment the current cluster. We use the current cluster instead of the sector, basically. And we read sector of the current cluster, and we place that into the buffer. All right. So if yeah, what I'm doing is just fixing all the errors. Not a big deal here. So sorry if I don't talk too much about what I'm doing. Okay, so yeah, and finally we have read next sector. So read sector from cluster, current cluster, and current sectoring cluster into the buffer. All right, I think I'm almost done here. So, oh, yeah, this was used to return how many bytes we've actually read, and it might be a good idea to save the original byte count to perform this calculation. So, original data equals data, and then we return the data minus original data, which should give it the size, the amount of data read. Okay, so we have, okay, we need to add this is directory as a parameter here in the open function. So open bool is directory. Okay, I'm gonna put these in fat file system. This is also something I forgot to do. Right, so where are you? Yeah, here. So inside the open function, yes, this is where we need to change a few things. Their entry. All right. So now we are calling this open correctly. What is file entry? Well, it's right here. Oh, file. It's called file. All right. What else do we have? So this open here. Yeah, instead of doing this ugly thing, all we need to do is just give it the cluster, the size, which would be 0. I think 0 is fine because we already handled this case, and is directory is true because this is the root directory, of course. And that's it. I've simplified. All right, let's see what else is left. Yeah, this get right. Now, right. We're not gonna support right at the moment. Writing is a bit more complicated, and yeah, we're not gonna support it at the moment. So I'm just gonna return 0 all the time. Okay, read and then write. All right, and last but not least, get the next file entry, the fun one. The funnest one of the fun ones. So the way this is gonna work is, in fact, I've changed my mind again. I'm returning such a big number is not ideal. Returning such a big structure. So what I'm gonna do is just make it a boolean. And have the caller of the function give me a file entry for me to fill. I think this is a pretty good approach. And I'm going to put this here as well in the file class. And let's make this public. Okay. And let's mark this as override and virtual. All right. And now for the implementation. And I don't think we even need previous here. Yeah, we don't actually need previous. So I'm just gonna delete it. Because we are using the position in the actual file to determine which is the next file entry. So we don't need the previous one, which is even simpler. And all right, same here in file. We don't need the previous entry. I'm gonna read this as a file, and just to make things more clear, I'm gonna call this read file entry, and I think this makes it a lot clearer what this function does. Okay. And yes, what we're gonna do here is simply read the next file entry. The only thing that I was thinking about doing here is adding support for and this is something that I've started here in my old implementation. Because a file will have both a short name and a long name. And these long file names, I've tried to implement them the last time, but I think I did not finish or something. I don't remember exactly. But yeah. Look. I now realize that it's 2 a.m. here, and it's been quite a long time. I've streamed for quite a long time. So I think we're gonna continue this another time. I'm gonna commit everything that I changed today. All right. Yeah, so I'm committing to this CPP refactoring branch in case you wanna check out the code. Yeah, I also have this fix for the toolchain. Some people have had this issue. Yeah. I'm not gonna add stage 2 old, and I'm gonna add all the core libraries that were changed, and I'm gonna add these scripts, but I'm not gonna add the old files. There's no point in doing that. Okay. Lot of work on that on a new fat driver. And there we go. Look, yeah, I'm gonna end streaming. If you have any questions, it would be a good time. I am answering a couple of questions if you have any. If not, then thank you very much, and I will see you the next time. I'm hoping to finish that video that I was mentioning about the first video about from the memory management videos. The first one will be about memory detection, and it will come out soon, I hope. I'll do my best to finish it as soon as possible. Now, yeah, if there are any questions, I am listening, and if there aren't, then thank you very much for watching, and I hope I didn't bore you too much with my implementation here. But yeah, refactoring is always tedious, it's always a lot of work, but the end result is worth it. The end result is always going to be worth it. We're going to be able to use this fat driver in the kernel. We're going to be able to, if we want to load, for example, like an initial RAM disk. This is something that Linux does. Basically, in the bootloader in stage 2, after you load the kernel, you can also load some other file. And then you tell the kernel, hey, I loaded this file for you, which is the initial RAM disk. The initial RAM disk is essentially a read-only file system which is basically read into memory at boot time. And it contains a couple of very important files. It contains the kernel modules for Linux. It contains, I don't know, some of the most important utilities. Things that you really want to have if, I don't know, maybe the hard drive fails, or not that the hard drive fails, but I don't know, maybe you fail to mount the hard drive, maybe something changed, or about the boot configuration. Yeah, it's a kind of like a recovery backup, but you also have drivers, you have the kernel modules, you have a lot of other extra things. You have configuration files that are used by the kernel. Yeah. Enough talking. Thank you very much for your attention. I hope this was interesting to you, and I'm doing my best here to make good code and explain everything that I'm doing. But yeah, sometimes I fail, sometimes I'm clumsy and I do things like this and think of 10 ways to do something, change my mind 10 times. Yeah, this is the nature of writing code. This is what happens when I write a lot of code. All right, see you next time. Thank you, and bye-bye.